Hey everybody, welcome back to GLSL for Pops and TouchDesigner. This is the fifth lesson, and today we're going to be looking at the GLSL Copy POP. Before we get into that, a few words about myself as I do. I'm a new media artist. I'm based in Brooklyn, New York. I create interactive installations that focus on exploring how human connection and perception is changing as technology becomes more and more ingrained in our lives. I think this is very topical, and it's what caused me to research a lot of the topics that I'm sharing now. Here are some past works. These are all using GLSL. I won't go through these in detail because I have in a bunch of the other videos, but just wanted to give some context for the larger scale types of applications. Now, for this lesson, we're going to be looking at the GLSL Copy POP, which is a very powerful new operator in the POPs family. And what it does is allow us to take an input geometry, a sphere, point, or something more complex, copy it a number of times, and using GLSL, define specific transformations, deformations, or properties of our copied geometry. Now, there's a copy pop that lets you do this, but the GLSL copy gives you a lot more control. And in my opinion, also is a little bit more straightforward to understand because, well, I just find it easier to read a few lines of code than to comb through all the different tabs of parameters and attributes and things like that. And then last but not least, the GLSL copy pop also lets us permute or change the vertices and primitive information of the copies, which is an added level of control in addition to the points. And so that really allows you to do pretty much anything you'd ever want to do. This is going to be the introduction to the copy pop, so we're going to look at the basic syntax, nothing incredibly intense, but we do have a pretty fun example, and I'm excited to get into that. So our example is going to be simple phyllotaxis today. Phyllotaxis describes how leaves or other plant organs are arranged around a stem, and you can see, I'm sure you've seen this countless times elsewhere, very complex forms get created out of what ends up being a pretty simple set of rules. And here's just a couple examples of that. I love this algorithm. I think there's many different ways of expression with it. And so I'm happy to use this as a good basic learning example for the GLSL copy pop. So how can we actually model phyllotaxis? Like I said, it's surprisingly easy. We can actually describe the entire pattern using just three parameters. The index of our element or organ. An organ, if you go back here, an organ could be either the petal or the leaf or the frond, whatever you call the piece of a cactus, as well as these little stamen in here. All of these are placed or grown really using the same property. And so often I use element or organ in place of point or something like that because each of these really represent a petal, a leaf, a frond, a stamen, etc. So we need the index, we need the spread constant, and then the angle of rotation. These three things are going to determine what the pattern looks like. Now, the most common angle of rotation is known as phi, the golden angle. That's 137.5 degrees. It is very well established, and it leads to exactly the types of patterns that we see here. Now, we can use these values to build up a Fermat spiral. And a Fermat spiral is going to transition these values to Cartesian coordinates in the XYZ domain. And so we can do that using the little formulas or relations that I have below. And that is calculating the radius and theta from these parameters, as I've already mentioned. So the radius will be the spread times the square root of the element number. And then theta will be the element number times our golden ratio. And then we'll use those with our classic r cosine theta, r sine theta to translate that into an x and y Cartesian coordinate, which we'll use to place the center of our organ. So what this means is, well, I think most of it should be pretty self-explanatory, except for this section here, theta equals n times phi. And what that means, as we can see in the diagram, each time we place an organ, we jump around the curve by phi. So we start with our first organ here, and then our second organ is 137.5 degrees this way. The same with the third, and the fourth, and the fifth, and the sixth, and so on and so forth. And the angle itself is what determines the precise placement and ultimate pattern composition of the result. So we are essentially building this up element by element and placing each element based on properties that are either shared among all elements or unique to that element specifically, which, along with the nicely parallelizable functions that comprise those relations, make it very easy to implement in GLSL. So basically, we just have to run this algorithm on every input point, or as we'll see, we'll copy a point for every organ that we need. Then we can calculate the point-specific spread and angle of rotation using those constants. And then finally, we can use our polar to Cartesian relation to find the XY space for the organ. And then we can define depth, opacity, and other things manually. So this completes kind of the conceptual part of our lesson. After this, I'm going to go back to TouchDesigner, and we're going to start rebuilding a GLSL implementation of this from scratch. So if you want to follow along, jump over to Patreon, subscribe. You can get access to this whole video, all the project files, all the rest of the course project files, and full videos from this course, as well as my full Introduction to GLSL and TouchDesigner course and dozens of other tutorials that I made. So go grab it there, support me, thank you. And for everybody that is currently supporting me, let's jump into things and take a look at TouchDesigner.